So for each of the sequences in this activity, what I asked your groups to do is, first of all, to investigate the sequence of terms itself. So what's happening to the numbers if you put commas in front of them. And then secondly, to compute some partial sums and make a, let's call it an informed estimate or an informed opinion about whether or not the infinite series would converge. If we tried to add up all infinitely many of the numbers that take these patterns, what happens to them? So let's start with 1 over n squared plus n. Where's the group that worked on that first example? Group over here. So what did you find, first of all, about the sequence 1 over n squared plus n? Was it convergent or divergent?
Convergent.
It was convergent. And how'd you know that?
Because there's n on the bottom and n's infinitely big.
Okay.
Infinitely big and here.
Great. So what this group observes is that if we take 1 over n squared plus n and we investigate the limit of that term as n approaches infinity, that this denominator grows without bound, so it becomes infinite, but the numerator stays the same. And so I have a finite number in the top of my fraction and an infinite number in the bottom of my fraction, and so that's a code word for 0. So we would say that this sequence is a convergent sequence. Whoops. Converges. There we go. Now, how about the series? What sort of speculation did you make about the series? In other words, if I were to add up the terms 1 over n squared plus n starting at 1 and going to infinity.
Converges.
So you speculated converges, and let me ask you why. So what did you notice?
As we were adding them up, they kept going. They had a pattern of being like 2 over 3, 3 over 4, 4 over 5.
Okay.
So eventually, if you keep doing that, it's going to become 1.
Okay. So in fact, more than just saying that this is convergent, you also made the speculation that this infinite series adds up to 1. Because your partial sums, as you say, were something like 2/3 followed by 3/4 followed by 4/5. Am I getting that right?
Yeah.
So those are your partial sums. So you predict that that converges to 1. Okay, cool. So one of the goals of what we do today is, at the very least, to be able to predict whether or not a series like this converges or diverges, let alone what it converges to. Now, this is a particular kind of series that we'll find out. We can actually determine its exact value just by applying a method that we applied on Friday, namely the method of partial fraction decomposition. Can actually shed some light on how this series works on a more rigorous standpoint. The numerical evidence suggests that it converges to 1, and we'll see some algebraic evidence for that today as well. All right, so now how about this other polynomial example, n squared plus n over 4n squared minus 3n plus 1? So what did you find, first of all, about the sequence, group B? Was the sequence convergent or was the sequence divergent?
Sequence was...
Well, I saw your group evaluating this limit.
Yeah.
How did you evaluate this limit? This is a question not just for group B, but for the rest of you. If we want to evaluate the limit of this sequence, n squared plus n over 4n squared minus 3n plus 1, if we just sort of imagine putting infinity in for n.
Yeah, we said it converges to 1/4.
I agree. So, but let's take a moment and just remember how we can evaluate a limit that looks like this. We have an infinity in the denominator because as n goes to infinity, 4n squared blows up, goes to infinity. And likewise in the numerator, we also have infinity. So this one is not as cut and dry as the first example. Because in the first example, we had 1 over infinity. Right? We had something in the numerator which would remain finite, while our denominator became infinite. In other words, we had a single pizza on the table, and we were cutting it into more and more and more different slices. And so the size of each slice is just going to go to 0. But in the second example, not only are we cutting our pizza into more slices, our pizza is also getting bigger every time. So we're cutting a bigger and bigger and bigger pizza into more and more and more different slices. So the question of how big each slice is impossible to answer right away. Because we don't know if the pizza is growing big so quickly that the even infinitely more slices is still going to have a finite value or not. So infinity over infinity is one of these enigmatic quantities in calculus. It's not undefined. Well, it technically is undefined. But we use a slightly different word for it. We call it indeterminate. Because a limit like this one, because the pizza is getting bigger and the number of slices are getting bigger without bound, a limit like this one has no value that we can discern immediately. We can't say that it's undefined. We can't say that the limit doesn't exist. We can just say that we don't know the answer yet. So let's call that a not yet limit. In other words, we have to do some additional work to determine what the value of this limit is. And what is that additional work? How do we remove an indeterminate limit in calculus? L'Hopital's rule. Well, how does L'Hopital's rule work? If I have an indeterminate limit, what am I supposed to do? According to L'Hopital's rule, the limit of a quotient that is indeterminate is the quotient of the limits. Sorry, is the limit of the derivatives of the quotient. That's really what I meant to say. So in other words, I'm going to take the numerator and the denominator and replace them by their derivatives instead. And then if that answer is still indeterminate, I might need to do it again. And if that answer is still indeterminate, I might need to do it again, and so on and so on. But let's do it the first time here. The derivative of n squared plus n. And the derivative of 4n squared minus 3n plus 1. 8n, thank you. 8n minus 3. Now what's this limit? Still indeterminate. It's still infinity on top, infinity on bottom when n tends to infinity. So because this is still indeterminate, what do I have to do? One more time. And one more time means that this becomes, we can make some space here, 2 over 8. And that is no longer indeterminate. As n goes to infinity, that approaches the value 2 over 8, better known as 1 over 4. Yeah, there we go. Cool. So L'Hopital's rule is actually an incredibly crucial tool for us, not just for doing what we did right here, but in tomorrow's class we'll come to an appreciation that L'Hopital's rule is actually about something bigger than just evaluating the limits of sequences. That L'Hopital's rule has the ability to sort of referee for us a race between two sequences that are approaching their limits. So remember, the question about whether a series converges is a question about how quickly its terms, its sequence of terms, approach 0. And L'Hopital's rule, as we'll see tomorrow, is able to referee that, to tell us whether one thing approaches 0 more quickly than another thing. But for today, at least, it's just a tool for helping us to evaluate this limit and helping us to conclude that this sequence does, in fact, converge. And it converges to the limit 1/4. What did you say about this series? Converges or diverges? You're informed.
I think it diverges. I think it just keeps getting bigger.
Okay. Why?
Besides proof on my calculator, I don't know.
Okay. So this is a good series for us to pick on because of what happens with its terms. Its terms are approaching 1/4. So imagine for a moment that we take the first few terms of the series. What were your first few terms? Can you list those out to me?
Sure.
1.
6/11.
6/11.
6/14.
6/14.
20/53.
20/53.
15/43.
15/43. Okay, so there are your first few terms. Now imagine that we go way, way, way out and look at some terms for n equals 1 trillion or something. What numbers are we going to see if we go far enough out in the terms of this sequence? What are they going to look like?
It's going to be...
They're going to look an awful lot like the limit of this sequence. So eventually, we're going to be adding numbers that are close to 1/4, plus 1/4, plus 1/4, plus 1/4, plus 1/4, plus 1/4, plus 1/4. So the sum keeps getting bigger by 1/4, and then another quarter, and then another quarter, and then another quarter, and then another quarter, and so on and so on. And so the speculation that this is a divergent series, I think, is spot on. Because no matter what, because my terms are still something close to 1/4, I'm going to keep adding that quarter infinitely many times, sort of, right, asymptotically. I'm adding a quarter infinitely many times. And if I do that, I'm going to get a series that diverges because the partial sums are going to keep increasing without bound. So that goes to infinity. So before we go to the next group, I want to make this observation into something concrete. Well, actually, this is a very concrete observation. Let's generalize it into something that we can use for other series as well. What was it about this sequence that definitely made its series diverge? So I'm going to write this out in a sentence here. The series summation n squared plus n over 4n squared minus 3n plus 1. Sum as n runs from 1 to infinity. And we said that this series diverges. And now I just want to complete the sentence here. Because what? What was it that told us that this was a divergent series? That 1/4, right? And what was that 1/4? Where did that 1/4 come from? The limit of what? The sequence. There we go. Remember, this is an it-free zone, so let's name everything what it is. Because the limit of the sequence, exactly, n squared plus n over 4n cubed minus, 4n squared minus 3n plus 1 was 1/4. And what was important about that number 1/4?
That's what the series is approaching.
That's what the sequence is approaching, which is why the series
Is adding
keeps
up.
blowing up. Exactly, you're right. So as we go far enough out in our sequence, eventually it looks like we're adding 1/4 plus 1/4 plus 1/4 plus 1/4 and so on. So let me flip this question around on you. What would we need to see up here in order for this series to have even a chance at converging? What are the terms, what does the sequence of the terms of a series have to do in order for that series to even have a chance at convergence?
Starting to level off.
They have to level off, but what do the terms of the sequence have to level off to? How do we avoid this plus a quarter, plus a quarter, plus a quarter, plus a quarter thing that happened in this example? What does the limit of the sequence have to be? The limit of the sequence has to be 0. In other words, to flip this example around and make it into something you can take to the bank, if an infinite series converges, summation of a sub n, and running from whatever to infinity, if a series converges, then there's no way that its terms can be doing what the terms of this series were doing. Namely, the terms of this series were approaching a limit that wasn't 0. And therefore, we're adding some number asymptotically that's not 0, infinitely many times, out at the end of our series, which is no good. So in order for a series to converge, we must have that the sequence a sub n has a limit, and namely, that limit has to be 0. So not only do we need to know that the sequence of terms converges, we need specifically to know that it converges to 0 in order for our series, our infinite series, to converge at all. We can use this test, I call it the Divergence for Dummies test, but it might be called the terms test or the limit of the terms test in a textbook. We can use it to determine whether a series converges or diverges, but we can't use it, we can't actually use it to determine whether a series converges. Because in the statement, we have to already know the series converges in order to conclude that its sequence of terms tends to 0. That doesn't sound very useful, because it would require us to already have the answer in front of us. So how in the world could this possibly be a useful theorem? Why do I call it divergence for dummies instead of convergence for dummies? again, take a look at the statement that we made about the series at the top of this slide here. We concluded that this series diverged because the limit of its terms was 1/4. In other words, we didn't use the divergence for dummies theorem in the forward direction. We used it in the backward direction. How recently have people in here taken their logic class? Math 180? Recently? Within the past year? So one of you tell me, what is the contrapositive of this statement? If a series converges, then its sequence of terms tends to 0. What's the contrapositive?
If a series does not
The sequence doesn't have a limit of 0, and it's divergent. And then the series diverges.
There we go. Awesome. So here's the contrapositive. Remember, the contrapositive of P implies Q is not Q implies not P. Not Q implies not P. So we have to negate both the hypothesis and the conclusion, both the antecedent and the consequent, and we have to reverse their implication. So if the sequence of terms does not approach 0, doesn't converge to 0, then the series must diverge. And that's the divergence for dummies test. Series diverges. It can't tell you whether or not a series, in fact, converges, because in order to tell us that a series converges, we have to already know that the series converges. It's not very useful. But its contrapositive has a lot of power. The contrapositive has the power to tell us that a series diverges merely by knowing that its sequence of terms doesn't converge to 0. And that's exactly how we use it here. The limit of our sequence was 1/4 and not 0. And that implies that the series diverges. So hanging on to this divergence for dummies test, let's go back to our table of what we were classifying a moment ago. And again, the divergence for dummies test now we can see right here. We made the conclusion that this series diverged because its sequence of terms had a limit, but that limit was not 0. So in order for a series to even have a chance at converging, its sequence of terms has to converge, and it has to converge to 0. So how about 1 over n times 2 to the n? Next group. First of all, what was the limit of your sequence, or was there a limit of your sequence?
0.
The limit of your sequence was 0, and how do you know that?
It's 1 over infinity.
Yeah, again, this looks a lot like 1 over infinity, and we're just going to think of 1 over infinity as being a code word for 0. Okay, so your sequence converge, and your sequence converges to 0. Conclusion? What can we say about this series? Well, again, I want to be as careful as possible about this. Because we can't immediately make that conclusion. Again, if the limit of this terms in the sequence was not 0, then we could say for sure that the series diverges. But just knowing that the limit of the sequence is 0 is not enough to guarantee that the series converges. So this is actually something separate. Here you had to look at the partial sums. And what did your partial sums suggest? Yeah, partial sums probably at least suggested that this is a convergent series. But again, we don't have that link. We can't conclude convergence just based on the terms going to 0. The terms going to 0 is a necessary condition for the convergence of a series. In other words, we need it to happen. But it's not sufficient. It's not enough to guarantee that the series converges. Instead, we have to know something else, like investigate the partial sums, as your group did, or perhaps apply the ratio test, as we'll do on Thursday, or make a comparison, as we're going to talk over the next couple of days, maybe take an integral, as we're going to do later today. But we have to do something else in order to guarantee that our series converges. Just knowing the terms go to 0 is not enough. But in the end, I will agree with your speculation that this is a convergent series, ultimately. But we haven't proven that yet. How about the last group? N factorial over 10 to the n. What happened with that sequence? Sequence. And since we know that the sequence of terms, n factorial over 10 to the n, diverges, what can we say about the series, the summation of n factorial over 10 to the n? It diverges. That one we can guarantee, based, again, on the terms test, or the Divergence for Dummies test, or whatever. So here we can use this criterion because our sequence of terms did not converge to 0. And anytime your sequence of terms does not converge to 0, your series must diverge. There's no other way. So any questions about this table?